Day 415 of doing a LeetCode problem every day until I get a job. All right, y'all, we're back again another day, another LeetCode problem where we're doing daily LeetCode problems. And today we have question number 2948, make lexicographically smallest array by swapping elements. The difficulty level is medium, but don't worry because you already know we're going to keep the solution as simple and easy to understand as possible. But before we get started, y'all, don't forget to like, comment, and subscribe. And if you need any new Apple AirPods, go ahead and check out that link in the description so you can get you some. Now let's see what the question says. You are given a zero-indexed array of positive integers nums and a positive integer limit. In one operation, you can choose any two indices I and j and swap nums of I and nums of j if the absolute value of nums of I minus nums of j is less than or equal to limit. Return the lexicographically smallest array that can be obtained by performing the operation any number of times. An array A is lexicographically smaller than an array B if in the first position where A and B differ, array A has an element that is less than the corresponding element in B. For example, the array of integers 2, 10, and 3 is lexicographically smaller than the array of integers 10, 2, and 3 because they differ at index 0, where 2 is less than 10. All right, y'all. So that seems like a lot to take in. So just in case you're having problems understanding the question, let's get into the examples just to make sure that we are doing this problem correctly. So before we get into the examples, though, y'all, I want to make sure we understand what lexicographically means, right? So an array with the smaller element at the first index differing position is considered lexicographically smaller, right? So for example, if say we have these two arrays, we have an array 1, 2, and 3, and then we also have an array 1, 2, and 4. As you can see, they are the same. Index 0 and index 1 are the same, right? But once we get to index 2, the element at index 2 is smaller in this first array than it is in this second array, right? So that means this first array is the lexicographically smaller array because once we get to index 2, 3 is less than the index 2 in this array, which is index 4. Or just to give you another example, say we have these two arrays, right? Say we have an array, sorry y'all, say we have an array and it's just 1 and 5, right? And then we also have an array that is 1, 3, 3, and 10. In this example, the one with the second array is smaller, right? So in this example, this array will be lexicographically smaller because once we get to index 1, 3 is less than 5, right? So since 3 is less than 5, that makes this array lexicographically smaller because once we get to the index, see, these indexes are the same, but index 0 is the same in both arrays. But once we get to an index where the numbers differ, where in this case we have 5 and we have 3, whichever array has the smaller, or whichever index has the smaller element in that array becomes the smallest lexicographically. So in this case, this would be the smaller lexicographically array. So just want to throw that in there just to make sure we understand what lexicographically smaller array means, because that's going to be important. Now let's get into the example. So in example 1, we have our input nums equals an array of integers 1, 5, 3, 9, and 8. The limit is 2. The output is the array of integers 1, 3, 5, 8, and 9. So before we get into the explanation, it's important that we understand we have to swap numbers, but we can only swap numbers if when we subtract these numbers from each other, the absolute value is less than or equal to 2, because the limit is 2 in this case. In other examples, it's whatever the limit is, but in this case, the limit is 2. So now let's go through the examples. So we apply the operation 2 times. The first time we swap nums at index 1 and nums at index 2, the array becomes the array of integers 1, 3, 5, 9, and 8. So first thing we're going to do is we're going to swap these two numbers, because when you subtract 5 from 3, you get 2. So that's equal to the limit. So that means it's a valid swap. We can swap them. So then we swap 5 and 3, and now we swap it right here, and now we have the array of integers 1, 3, 5, 9, and 8 instead of 1, 5, 3, 9, and 8, right? So we swap the 3 and the 5. We're one step closer to being the lexicographically smallest array that we can create. Next, we're going to swap nums at index 3 and nums at index 4. This array becomes 1, 3, 5, 8, and 9. So now we're going to swap these two numbers. And it's a valid swap because when you subtract 9 from 8 or 8 from 9, the absolute value is still going to be 1, and 1 is less than 2, right? Remember, it has to be less than or equal to the limit, and in this case it's less than the limit, so that makes it a valid swap as well. So now we have 1, 3, 5, 8, and 9. We cannot obtain a lexicographically smaller array by applying any more operations. Note that it is possible to get the same result by doing different operations. So in the end, this is our smallest lexicographically ordered array, so that's what we are going to return. Boom, and that's how we got it. That's how we were able to achieve those swaps, because each swap was less than or equal to the limit. The absolute value of each swap was less than or equal to the limit. So let's go to example 2, where because this may seem misleading, because you may think, oh, it's just a sorted array. We just took this array and we sorted it, and it's now lexicographically smallest array. But let's look at example 2, where it may not be a sorted array, but it still is the lexicographically smallest array that we can create. So in example 2, we have the input nums equals an array of integers 1, 7, 6, 18, 2, and 1. This time the limit is 3. The output becomes 1, 6, 7, 18, 1, and 2. So once again, we have to remember each time we swap, when we subtract those numbers from each other, the absolute value has to be less than or equal to 3. So let's go through the explanation. First, we're going to apply the operation 3 times. First, we're going to swap nums at index 1 and nums at index 2. The array becomes 1, 6, 7, 18, 2, and 1. So first, we're going to swap this right here, the 7 and the 6, right? So that's going to put the smaller element in front of the larger element, which is going to get us one step closer to being lexicographically smallest array. So, and that works because 7 minus 6 is 3, 6 minus 7 would be 7 minus 6 is 1, 6 minus 7 would be -1, but the absolute value of -1 is 1. So either way, it fits the requirement, is less than the limit, so we could go on to the next operation. Now we're going to swap it in nums index 0 with nums at index 4, and the array becomes 2, 6, 7, 8, 1, and 1. So now we're going to swap this 1 and this 2, right? Boom. So now the 2 comes in the front and the 1 comes towards the end. Now you might be wondering, why would we swap the 2 with the 1 when 1 is smaller? Don't worry, we're going to get to that as we get further down, as we keep going through the code, or we keep going through the swaps, right? But right now we have the 2 right here and we put the 1 right here. But now we are going to swap at index 0 and index 5. So now we're going to swap that 2 with that last 1, and this array becomes 1, 6, 7, 18, 1, and 2. So now we swap this one, we're swapping this 1, we're swapping this 2 with this 1, right? That fits the requirements. It's a valid swap because the difference is less than 3. So now we swap that. Now we're back and have the 1 at the beginning, and we have the 2 at the end. Now remember, there is possible ways to get the same result with different operations, but in this case, that's how they did it. That's what we're going with. So now we have the 1 and 2. We have 1, 6, 7, 18, 1, and 2. Now it's important to realize that, as you notice, this 18 didn't move, right? This 18 is still in the same index, which there's nothing we can do about it. Why is there nothing we can do about this 18? Because there's no element in this array that we can swap from 18 where the difference would be less than 3, or 3 equal to less than or equal to 3. Like if we swap 7 to 18, the difference would be 9. If we swap 6 and 8, 7 and 18, the difference would be 11. If we swap 6 and 18, the difference would be 12. And all 2 and 18, you already know that's not going to work. And 1 and 18, that's not going to work. So 18 stays the same because we're not able to swap it with any elements where the elements or the difference between those elements will be less than or equal to 3. So 18 stays the same. And that's important because now you see why we cannot, it's not as simple as just sorting the array, right? It's not always going to be just sorting the array if the difference between two elements end up being greater than the limit. So that's why this 18 stayed the same. We were able to swap all of the other elements though, which was allowed us to get this output of 1, 6, 7, 18, 1, and 2, which is the smallest possible lexicographically array that we can apply or that we can create. So let's look at example 3. It has a lot of the same principles as example 2, where, as you can see just off the top, we're not going to be able to swap these 3 numbers right here because the difference. Or really, we're not able to swap any numbers in the whole array because of the difference will be greater than 3 or greater than the limit. But let's go through it anyway because that's what it's here for, so we all can learn, just in case people are still having trouble with understanding these examples. So in example 3, we have the input nums equals an array of integers 1, 7, 28, 19, and 10. This time the limit is 3. The output is the same array 1, 7, 28, 19, and 10. It says the array 1, 7, 28, 19, and 10 is the lexicographically smallest array we can obtain because we cannot apply the operation on any 2 indices. So as you can see, all of these indices have a difference that's greater than 3. You might could say we could swap this 7 and this 10, but if we put the 10 all the way up here and the 7 over here, that's not lexicographically smaller than this array that we already have. We already have an array that is lexicographically smaller than that, so we could just stay with the array that we have. There's no need to change anything. So I hope that made sense to y'all, and now that we understand the question, let's get into the fun part, the actual solution. Solution is not that difficult at all. Now, the first thing we are going to do is we're going to enumerate nums with the original indices and sort them by value or sort them in ascending order. This is going to help us know which smaller values are available to move forward. So for that, we're just going to say let sorted nums equal nums dot enumerated. Now remember this enumerated, this is going to get us the index and the value at that index. Then we're going to say dot sorted. Then we're going to open up the brackets and we're going to say $0 dot element. We got to put dot element because we enumerated it. So dot element is less than $1 dot element. And once again, this is going to sort them in ascending order. Now we're going to declare a variable, and it's going to be an array that marks the starting index of each swap group in sorted nums. So for that, we can come right here, declare a variable, we call it groups, and that's going to be an array of integers. So square bracket integer, and put the 2 parentheses outside. Now we need an array to record the group index that each original position belongs to. So for that, we declare another variable. We call this nums group, and we can set that equal to an array of integers. And we'll open up the parentheses. This is going to be repeating. So this is just the default value for the array of integers. It's going to have repeating zeros, comma, count, colon, up to nums dot count, whatever that may be. Then we need a variable for the index for the current group, and we're going to increment it when starting a new group. So we can come underneath this, we declare a variable called group end and set that equal to -1. Boom. Now we need a variable that's going to track the last number seen during the group creation. So we could just declare a variable called last num and set that equal to int dot min, just like that. Now, step 1, we're going to partition the sorted elements into groups based on the limit constraint. So we come underneath this, we could say for open up the parentheses, because we're dealing with the enumerated again. We're going to say I, comma, open up more parentheses. We're going to say original end, comma, num. Then we're going to come outside those two parentheses. We're going to say in sorted nums dot enumerated. Once again, that's going to get us the index and the value at that index. And if the current value is too far from the last, that means we cannot swap with the previous group. So we're going to say if num is greater than last num plus limit, then we're going to start a new group at index I. So we're going to open up the brackets and we're going to say groups dot append, open up the parentheses I. Then we're going to increment groups end by 1. So we're going to say groups, sorry, let me put an S up there. Or now it could just be like this. We could say group end plus equals 1, just like that. Now we need to record which group this original index belongs to. So for that, we come underneath this. We could say nums group, open up the square brackets, original end equals group end, just like that. Then we're going to update the last number seen. So we're going to come underneath that and we're going to say last num equals num. Boom. Now we need to create our final result array, which will be, so remember, our result array or our output is an array. So we need to create that array for us to store our result in. So we could declare a variable called res, and we could set that equal to an array of integers. Come outside of that, put the parentheses. Boom. Then we're going to say res dot reserve capacity, open up the parentheses, nums dot count, just like that. Oh, sorry, y'all. Just like that. Boom. Now we need to reconstruct the result using the smallest available number from each group. So we're going to say for, open up the parentheses, num, comma, group, end ind. We're going to say n, come outside the parentheses, n, zip, open up the parentheses, nums, comma, nums, group, come outside of that, open up the brackets, and we're going to use the next smallest number from this group and append it to the result. So we're going to say res.append, open up the parentheses, sorted nums, open up the square bracket, groups, open up the square bracket again, group end, ind, come outside both of those square brackets, still inside the parentheses, and we're going to say dot element, just like that. Now we need to move the group pointer forward to use the next smallest for future members. So we're going to say, come underneath that, we're going to say groups, square bracket, group ind, and we're going to increment it by saying plus equals 1. Just like that. Now we need to return the final lexicographically smallest array by coming underneath this for loop, and we could just say return res. Just like that, y'all. That should be all she wrote. Let's give it a run before we submit it. Make sure it works properly. Okay, cannot find original and original. I don't know. Let's just copy and paste this and see if that works. Might have spelled original and maybe I spelled it wrong. Let's run it. Let's run it, y'all. See if that works. Copy and paste just for the spelling. That's what I'm talking about. It's accepted. So let's go ahead and submit it. Make sure it's still accepted after we submit it. Ooh, look at that, y'all. 24 milliseconds beats 100% of users with Swift. That's what I'm talking about. Those are the numbers that I like to see. Now, before we go, y'all, make sure you get one more look at the code. This is the top part. This is the bottom part. And yeah, y'all, with that being said, make sure you read it, learn it, love it. And I hope y'all learned something today. And I hope to see y'all here tomorrow for another day, another LeetCode problem. See y'all then.